Welcome to ChemVid. Today we're going to talk about forces of attraction and the difference between intramolecular forces and intermolecular forces. Okay, so let's start out with the difference between inter and intra. If you know about interstates, interstates go across states. They go across the nation. Whereas an intrastate is like a highway that stays within a state. Well, molecules and everything, they're the same things. Intramolecular forces are bonds within a molecule. Okay, so when you look at CO2 or H2O or any one molecule, it's the bonds that hold them together. There are three of them: ionic, covalent, and metallic. Those were the ones we discussed earlier. Okay, so if you look over here at my cute little comic, you can see that ionic transfers electrons. See how he's giving that away. Covalent share electrons. And metallic, well, they have a sea of electrons that allows them to share and be happy. I'm not exactly how that works out with this comic, but that we know that to be true. This comic's a little maybe flawed. So those are our intramolecular forces, the bonds within a molecule. So what I want you to do is I want you to take a few moments and I want you to fill in this table. How do we model or how do we show ionic, covalent, and metallic bonding? Why are they attracted to one another? Give me an example and tell me who is the strongest, the weakest, and then the middle. Go ahead. Okay, now hopefully you tried that out. Let's review. Ionic, we have this lattice structure. Covalent, share electrons. We use Lewis dots to show that. And metallic has a sea of electrons. Cations and anions are attracted to one another in ionic. The nuclei pull the shared electrons together, creating bonds in covalent. And metallic cations have those mobile electrons. We call it a sea of electrons and delocalized electrons. And that gives all of our compounds stability. The example they have in the book is salt, NaCl, hydrogen, which is hydrogen gas, and iron, which is a very common metal. So, did you get the strengths right? Ionic and metallic should be about the same strength. They both have very high melting points and boiling points. They are very strong due to their lattice structures. And so it really just depends upon the sample who would be strongest. But covalent is definitely the weakest, with low melting points, low boiling points, and they're very easy to get into another phase. So that's it for intramolecular forces. That is our review. So let's start with let's move on to intermolecular forces. All right. Intermolecular forces are the forces between molecules. Okay? So, whenever you're talking about any type of interaction between like a water and another water, or water and methane, or CO2 and water, all those are between molecules. So, in order to have intermolecular forces, you have to have two of the same molecules. Okay, so there are four big types of intermolecular forces that control how molecules behave with one another. These four types are London dispersion or van der Waals. They're the same thing, but two guys helped to discover it, so now the term has two names. The second one is dipole-dipole. The third one is hydrogen bonding, and the fourth is ion dipole. Okay, so let's start with dispersion forces. Dispersion forces are instantaneous attractions between any nonpolar molecule. So, thinking about it, if I have a blob that is neutral, let's go over here. I have a blob that has a nucleus, so it's got a positive charge. And then it's got its electron density all around it. And then I have another blob with a positive charge and electrons around it. These guys are technically nonpolar, right? I can't separate the charges. However, if I move them close enough to each other, these electrons right here are going to start repelling each other. And therefore, we get this odd kind of a bean shape where the electrons are moving away from the other electrons so that they don't have to be near each other. So the reason why we call this instantaneous attractions is because these attractions aren't always there. They don't always exist. It only exists when you put two nonpolar things together and it forces them to create these instantaneous dipoles. Okay? Alright, so this is your model. Go ahead and draw that. And then, so what do they occur in? They occur in all particles. Okay? So polar or nonpolar or not, when you put two things together, the electron density is going to rearrange itself so that it doesn't have to be so close. Okay? However, we mainly think of these guys as being part of nonpolar molecules. Okay? And because they are instantaneous, because they don't actually have a charge or an attraction, we call these are our weakest intermolecular forces. So thinking about our strength, as the mass increases, what's going to happen to the strength? Well, as I increase the mass, that means that I have a larger electronic force or a larger nuclear force, and therefore that means I have a stronger attraction because it's kind of like the magnet situation again. If I have more negative and more positive charge, then they are stronger and can hold together. So as mass increases, so does strength. That doesn't fit. But strength also increases, okay? So strength increases as mass increases because the bigger you are, the stronger your instantaneous dipole can be. Alright, our next intermolecular force is called dipole-dipole. If you recall, when we were drawing polar compounds, we had a positive side and a negative side, and you can draw a line straight through them. That's how we knew they were polar. Well, if you recall, this change or this separation in charges is also known as a dipole. We drew it with an arrow. The arrow pointed to the more electronegative atom. So in this case, I would draw the arrow towards my fluorine because it's negative. So the reason why this is called dipole-dipole is because it is a permanent attraction. This polar molecule will always have a positive and a negative side. And so therefore, this attraction never goes away. It's always there. So we call it permanent. Okay? It occurs in all polar molecules. All right? And we tell if something is polar based on the electronegativity and if there is a separation in charge. Okay? All right, so strength. As far as strength goes, the bigger my charge, the stronger my attraction is. So the more polar a compound is, or a molecule is, the stronger the attraction is going to be. Okay? So these guys are stronger than van der Waals or London dispersion because they have permanent charges. And if I'm just trying to compare two dipole-dipole, the more the polarity there is, the stronger I am. Alright, the next one is hydrogen bonding. Now, hopefully you guys have learned about this in biology. It's the reason why water behaves so awesomely. But hydrogen bonding is an attraction. Don't let the name fool you. Remember, the only types of bonds there are metallic, ionic, and covalent. This is an attraction. But the reason why it's called hydrogen bonding is because this attraction is so strong, we wanted to give it a special name. Okay? So, not a bond, but very strong attraction. Now, this attraction occurs between polar molecules that have a nitrogen, an oxygen, or a fluorine, and they're attracted to an hydrogen. So if I look at water, water is the key example for hydrogen bonding. Oxygen is attached to a hydrogen, and because hydrogen is so little, oxygen can grab much more of the electrons, so it makes this delta negative charge really strong. And then it's of course attracted to the other hydrogen on another water molecule that has a really strong positive charge. So unlike dipole-dipole, where you have a permanent change, you have a positive and a negative side, because hydrogen is so weak and oxygen, nitrogen, and fluorine are so electronegative, it causes an even stronger attraction, so that's why they get their own name or own category. Okay? So let's look. This occurs mainly in water. Water is our biggest one, and that's what allows us to live and to have food and to do all the wonderful things we need to. But it occurs anywhere where an H is attached to an N, an O, or an F. That's where hydrogen bonding occurs. I call it H-NOF. So hydrogen bonding can occur in H-NOF. All right, as far as strength goes, like I said before, because hydrogen is so small and our electronegative atoms have pulled the electrons away so greatly, this is a really strong intermolecular force. It's stronger than dipole-dipole, and it's much, much stronger than London dispersion forces. Okay? And of course, with this one as well, since fluorine is most electronegative, he's going to be the strongest, and nitrogen is going to be the weakest of these three. Okay? But all three of them are very, very strong compared to our other intermolecular forces. So why is this important, you say? Well, hydrogen bonding is what keeps our DNA attached to one another so that we can live. So if you're here thinking, why am I learning about this? This isn't even important to me. Thank hydrogen bonding for keeping you alive. All right? Very important. Okay. Our last intermolecular force is ion dipole. Now, if you look at ion dipole, you know what an ion is, right? An ion is anything that has a charge, like sodium. Bam. It's got a charge, that's an ion. We know that dipole means polar, correct? So an ion-dipole interaction is an attraction between an ion and a polar molecule. Okay? So any ion and any polar molecule are going to come together, and the positive side of my polar molecule will be attracted to an anion, and the negative side of my polar molecule will be attracted to a cation. Okay? Where does this occur? Well, between any polar molecule and any ion. Because ions have that charge, your polar molecule is going to be attracted. You guys have seen this in salt water. We drew this before. So we have our sodium with a cation, and the water surrounds the sodium and pulls the sodium and the chlorine apart. If you think about it, when you put salt in water, the reason why salt dissociates in water is because the attraction between a polar molecule and an ion is stronger than the attraction between a water and a water. Therefore, ion dipole is the strongest out of all of my intermolecular forces, because it has not only a dipole or a permanent dipole, but it also has a real charge in the ion. This is a completely positive charge and a completely negative charge. So this makes for one strong attraction. Okay? So ion dipole is our strongest attraction. So, for your homework, I would like you to try and put your intramolecular forces and your intermolecular forces in order in these boxes from weakest to strongest. All right? Thanks for tuning in. Have a wonderful rest of your day, and we'll see you next time.